So the electromagnetic radiation from the sun has left the sun and now it's heading towards Earth. Well, what happens to it next? Well, this diagram here summarizes what happens to it. As it's coming down, about 3% of it is absorbed by the ozone. And of course, that's the harmful ultraviolet rays that we're concerned with. So that's a very good thing. About another 25% of it is reflected from the clouds. So that never reaches the surface of the Earth. It's just basically the light reflecting off the clouds. Another 19% of it is absorbed by dust and gas in the atmosphere. And the remainder of the electromagnetic energy gets to the surface of the Earth, the remainder of the solar radiation. This is going to include about 45% that's absorbed into the ground and will be re-radiated outward by the Earth, and about 8% that's directly reflected from the ground off of the surface of the Earth and back towards where we may have satellites in the sky or other sensors in the sky that is able to record that information. So of all that energy that comes in, it's just about 8% that's reflected. As far as those different things that happen in the atmosphere, let's take a little closer look at that as far as what's really changing as it moves through the atmosphere. This really depends on the wavelength of the radiation. So here we see the different wavelengths of the radiation. Here's the visible portion of the electromagnetic spectrum. Once again, as we move in this direction here, we would be getting into infrared and then into other thermal type things out here until we get out to microwaves out here. And then in this direction here, we would be going through ultraviolet and then things like X-rays and gamma rays way out in this direction here. But what's shown here is what is being blocked by the atmosphere, which is being shown by this brown stipple pattern, and where the electromagnetic radiation is able to get through. So once again, not only because the sun behaves like a black body, is that the peak of where radiant energy is coming from the sun, but it also happens to be a place where little of that energy is absorbed by our atmosphere. So we're able to get a lot of that to the surface, and a lot of that is what's reflecting back off the surface of the Earth to our sensors. So a lot of the sensors here, like photography, aerial photography, and multispectral scanners on satellites, are kind of cued in to measure this energy because this is such a good place to measure it. Sometimes we call these atmospheric windows because these are the areas shown in white here, such as here, out here, some of these areas here and here and here. These are the areas where that wavelength of the electromagnetic spectrum is able to make it through the atmosphere and get to the surface of the Earth. And so those are very important areas and what our sensors are built to report on. Once that reaches the surface of the Earth, whatever we're trying to sense, whether it's a field of corn or something else, we can think of that as the object that we're trying to sense or the target. And what we see then is that radiation that makes it through the atmosphere does three things. Some of it is absorbed. It can also be transmitted through, if there's another layer below, such as water might just transmit the energy through to the ground underneath, or it can be reflected. And we're going to talk next about this reflected radiation because it behaves differently for different wavelengths of light. And one easy way to see this is just the color of the object or the color of the target that we're looking at. So in this example here, we're not looking at the full electromagnetic spectrum, we're just looking at a green wavelength, a blue wavelength, and a red wavelength, as if that had already come through a spectrum. So if all of those three wavelengths hit a red target or a red object, the blue and the green will be absorbed, but the red is actually reflected back. And if it's reflected to our eye, that's why, it sounds simple, but that's why red objects look red. In the same way, if we have a green object, the red and blue are being absorbed by the object and the green light is being reflected. And if we have blue, the red and the green are being absorbed and the blue is being reflected. And we can see that if we have a cyan object, that's a mixture of green and blue. So the red would be absorbed here and both the green and blue light would be reflected. The same with magenta, the red and blue lights are the ones reflected, wavelengths. And with yellow, the red and the green wavelengths are the are the ones that are reflected off that object. And that's what we would see with our eyes. That's what we would see if we take a picture of it. And that's also what the sensors on the satellite would see when they go to measure all of these. They wouldn't see, in this example here, they wouldn't see anything in the blue portion of the electromagnetic spectrum for what they're measuring for this object, but they would see spikes in the red and the green portion. And using all of these responses at different wavelengths, we can see the wavelength is varying here. We can come up with what we call spectral signatures for different objects on the ground. So in this case here, we're just trying to compare soil, which is shown by this dashed dotted line here, with soybean crop, which is shown by this solid line here. If we were looking at sensors in certain portions of the electromagnetic spectrum, if we were measuring what the values were, we might have a hard time distinguishing those when these two lines are right on top of each other. But if we had one sensor here, and one sensor here, and one sensor here, we would see differences in the response from the two different types of objects, from soil and soybeans. So here, the soybeans would have a higher value, the soil would have a lower value, and here it would just be the opposite. So this is one of the ways that we use this reflected electromagnetic radiation in order to determine what's on the ground.